So what I'm going to do is talk about machine learning, like neural network models. So convolutional neural networks is something you'll run across a lot because you'll see that everywhere, everything from text analysis to image analysis to video analysis to audio analysis. It's used everywhere. So it's one of the fundamental things. So for example, with text analysis, you're dealing with a one-dimensional convolutional network. Image is typically 2. If you're dealing with time series data, it could be 3 or more. So for example, handwriting recognition is a multi-dimensional convolutional network. It's not a 3-dimensional one even. It can be fairly complex. So this is inspired by the cat's visual cortex. And so when a human being looks at something, we're actually spend most of our lives like hallucinating. So that's actually, we don't actually see things. What our brains do is that it fills in the gaps. So we see a little bit of something and our brains just complete the picture. So everything looks the same. Everything looks like we see the whole thing, but it's actually your brain filling in a lot of the gaps, which is why you get optical illusions sometimes, because your brain is trying very hard to fill in the gaps, but it can't because it doesn't make sense. It doesn't match something that it really sees. So convolutional neural networks are basically designed around the cat's vision. So cats have a couple of things, well, humans do too. So for example, we're scale invariant. So scale invariant means if something is close up or something is far away, we can still say it's the same object. So if somebody, for example, is like 10 meters away, even though they're smaller at that distance, you still know that that's human. We're also rotationally invariant, which means that if somebody's lying down versus standing up, we still know it's the same person. Although sometimes dogs get confused, actually. So in general, like, and they're also translational invariants. So we have rotational invariance, scale invariance, and translational invariance. Translational invariance means if somebody's standing here versus there, we still know that that's the same person. So our brains are very good at those kind of things. And then we have other things where we're relatively invariant too. Lighting is another. So if it's dark versus bright, we know it's the same person. Even to some extent color. It's like if somebody's wearing a pink shirt one day or a red shirt the other, or green shirt the other day, we still know it's the same person. So because we're able to like pick up things. So this was sort of the inspiration behind convolutional neural networks, to kind of like how do you build a neural network that compensates for all of that invariance. So it was developed by Yann LeCun. I think it was in 2002 or 2003. So it's actually it's been around for a long time. And it was one of the first times that people were able to actually accurately model, were actually able to build neural networks that could recognize objects and things like that. So some of the standard methods would be things like CIFAR10. So they're standard data sets to see how good your models are, CIFAR10, CIFAR100. As you increase the dimensions in a convolutional neural network, you can model more and more complex things. So you can add time elements, space elements, you can add all kinds of things like that. So what is a convolution? That is a convolution. So basically a convolution is, think about it as an operation that takes place so you're translating, actually it's easier to illustrate. So basically what it is so if you have a function f, so think about f as being like a big picture. So then what you have g is basically it's a weighting function that you're going over the entire space. So what this does is so it's more complicated than what it should be. But what this basically says is that the value at this point, this would be the equivalent of one-dimensional convolution because it's just x. So what that's basically saying is that I'm translating this weighting function across all of the values of this function that this function can assume. between negative infinity and positive infinity. So literally it's taking a transformation and then sliding it all the way through and then getting the cumulative effect of that translation. So that's what a convolution is. So the way to think about it is that if you have an image, you can have a convolution which basically distorts part of that image, and then you kind of keep sliding it across, and you keep getting, like, you distort that part of the image. So this distortion is it's called a kernel. You can also call it a convolutional operator. But basically it's something where you're making changes to one part of it and then just sliding those changes across. So let's basically give you a really simple example. So suppose I have a very simple image, and in this case, an image. What is an image? Basically, it's just it is it's a pixel value. So let's say it's just a pure black and white image. In this case, that's there. So the way you probably see it is that suppose you were to draw this picture, then it would be something like this. So it's very simple, right? So that's what the image looks like. So actually, sorry, I should say that's the image there. That's the image. That was the first vector, or the first matrix was the convolution. So the image in this case is a 3x3 image, and it looks like this. And down here, it's like, right. So that's what the picture looks like. Not particularly creative, but it's a picture. And it assumes two possible values, black or white. So now what I'm doing is I'm going to, how do you train an AI to recognize these kind of images? So what you want to do is extract features that the AI can learn. So the way to do that is you, for example, pick an operator, and what this operator will do is you will scan this image with that operator. Basically, you start with this and then slide it over, then slide it over, slide it over. And based on that, you construct something called a feature map. And the feature map is essentially a map where you've run that operator through that image. So in this case, the feature map would be, so let's say the operator is 1, 1, 1, 1, 0. So when I run this through this, so how do I read it? So in this case, the operator is going to be like an element-wise multiplication, so which means that if you go there, so it's basically, this is the operator, it's 1, 1, 0, 1. So what I'm doing is I'm doing an element multiplication, so this is a 1, 1 times 1, 1 times 1, 1 times 1, and 0 times 0. So then it's basically, you have 3, and then you add them up together. So you have a new feature map. You have a feature map where the first number is 3. Then the next part, then you slide it over by a bit, and then now you do the same thing. So you have, in this case, 1 times 1, 0 times 1, 1 times 1, and 1 times 0. So if you add that up, then what that becomes is 2, right? So it's basically just that and that together. And then if you do the same, then you get 1 and 3. So that's what's known as a feature map. And so typically, there are many possible convolutions. This is one convolution. If you have a real image, like a really complex image, you could have convolutions that are doing edge detection. You can have convolutions that are blurring things. You have convolutions that are distorting things. You have a whole bunch of kernels that you're essentially applying to that. So the end outcome is that if you have a picture of a dog, you have a ton of these feature maps. And each of these feature maps, how do they come about? They came about through some sort of a convolution operator like that. So you can have one. So in this case, I have no idea what this did to that particular image. But for example, it would be, you could have a kernel that distorts part of that image. So it basically blurs it and then scans it through and just blurs everything else. You could have something where it finds edges and again scans through that and determines all the edges. There are all kinds of convolutions like that. So blurring, for example, could give you a color, the rough color profile of that part. So maybe blurring can be used for color detection, for roughly determining colors. Edge detection is obviously shapes, and so you're applying all these different kinds of feature maps together. So once you've actually done that, you operate you essentially get, you do a ReLU operation. So ReLU, remember, it's a rectifying linear unit. It's one of these things that I never remember until I see it. But what a ReLU is basically, it's an activation function. So you'll remember I showed you back when it's an activation function. And what ReLU does is that, the way to see it is that it's 0 until you hit a certain value, and then it increases linearly. So which basically means that for any negative value, it's 0. Any positive value is the actual value itself. So then if we apply that, so for example, if you have a feature map like this, if you have -1, 3, 2, and 1, the -1 just gets mapped to 0, and then the rest are basically the original value. So what that does is it eliminates all negative values from my system, from my picture. So the next thing is basically where you take the most important aspects of, so you take the most interesting element of that feature. So now I can't do it with this because this is so simple. The most interesting feature is this. So what I'm going to do is you take a bigger component. So the same thing is, what I'll do is, this is actually already a feature map, but let me just get you bigger. So this is going to be painful to draw. Okay, so suppose I have this, and I have a very simple, let's say, a identity. So, and I basically have like 1, 1, 0, 0, 0, 0, 1, 0. I should just make it interesting. Let's do 3. So, yeah, so it's just, so it'll be, and then maybe 1, 1, 0, 0, 0, 1, 1, or something like that. Okay, so when I do this, when I apply this, I'll actually get some sort of a feature map. So the feature map in this case will be, it'll be 2. And then you slide it over by 1, and it's going to be 1. Then you slide it over by 1 again, it'll be 1. And then you kind of like go down, in which case then it's going to be 2, yep. And then slide it over by 1, that's going to be 2. Slide it over by 1, that's going to be 0. And move down again, and then it's going to be 3. Slide it over by 1, it's going to be 3. And then the last one is 2. So that would be my feature map. Oh, yeah, sorry. Yeah, that's right. This is 2.
Yes, back row.
Yeah, exactly. So it's 2, yes. So then what I want to do, the next thing I would like to do is I take a region, and I'm going to take the most significant element of it. So there's an operator which is, it's called max pooling. So what max pooling does is it takes the most significant aspect of that part of the image. So in this case, the most significant it's the maximum number, and it's going to be 2. So if I then kind of apply max pooling to this, I get 2, then slide it over by 1, and then I get, again, 2. Slide it down by 1, I get 3, and then slide it across, I get 3 as well. So what that'll do is that extracts the most significant element of each part of the, by the way, I didn't apply a ReLU operator because I didn't need to in this case. So you'll always see with a convolutional network, the process is apply the convolution, you get this, then you do immediately right after you do max pooling. And the stride is basically how much you slide the different windows over. So the thing that max pooling will do is it will remove non-essential pieces or insignificant pieces. So if you're applying, for example, if your convolution is a rotation, then what it'll do is that things that are not relevant in that rotation, it will eliminate those. If it's applying if there's like a scaling element to it, so an example would be if you have a human, which is like close by, and then a human that's far away. So the way that you can actually do this is that with max pooling, it will still you'll still start to extract out the most important elements, and you'll start to see that both of them have sort of similar representation in some scale. Because the next thing we're going to do is you do max pooling, so and then you reapply the whole thing again. So when I take this, once I do the max pooling, I apply a convolution to this again, and do max pooling and so on and so on. So why do I need to do that? When I do that, that captures the scale invariance. It also captures things like rotational invariance, blurring invariance, all these things, color invariance, all these things are basically captured on many different scales by continuously breaking down my image and applying max pooling and so on. So basically that's the overall convolutional process. And so you keep breaking and breaking and breaking it down. But you notice that during this entire process, the question is, well, where am I actually learning anything? Like, it doesn't appear that there's no machine learning involved. This is just simply operating a set of standard operators. Well, once I've done all of these things, I've maybe gone through like several max pooling convolutions and so on, then what I can then do is I can assemble all of that data into a vector. So the thing about all matrices, so all neural networks are ultimately vector operations. So you have your input x0 to xn, and you have a matrix which basically goes a1 to, so a0, 0 to a0n, and then whatever, it can go am0 to amn, right? So that's basically, that's kind of like the starting point for all neural networks. So what's really going on is that with a neural network, everything gets ultimately mapped to a vector. So no matter how complex the neural network problem is, it's always mapped to a vector in the end.